Ladies and gentlemen, please welcome Senior Staff Engineer, Pivotal, Mark Fisher, and Vice President of Technology, Pivotal, Cornelia Davis.
Hello. It is such a pleasure here to be with you all again this morning. Just by way of a little bit of a warning, I want you to know that in today's talk, Mark and I, what we really want you to come away with is just a different way of thinking. So that's what we're really aiming for. So let's jump right in. When I started my career about 30 years ago, yes, I am that old. I have the gray hair to show for it. Programming systems was relatively easy. I actually started in aerospace working on embedded systems, and multiprocessors weren't even the norm. But what's happened now is that there's so much complexity in the problems that we're solving today, and this is a fantastic picture of some clouds around Jupiter, is that we are now applying computing to problems that are greater in terms of the complexity. John von Neumann was one of the very first people to take computing and apply it to the task of weather prediction. And I've heard it said that John von Neumann actually believed that we would get computing power to the level where we could 100% predict the weather. Well, we know that isn't the case, but I would assert that John wasn't naive with respect. He wasn't overestimating the amount of computing power. In fact, he probably underestimated it. But what he probably did was he underestimated the level of complexity that there is in modeling something like weather predictions. So what we're doing today is that maybe there's some new problems we're trying to solve, although when Mark and I were chatting about it before, we kind of realized that these problems have always existed, but what's happening now as technologists, as software professionals, is that we are starting to apply software to problems with such tremendous complexity that we didn't used to do before. And what that means is that we need to use new tools and new approaches. And it's that we're going to talk about today. Now, we're not going to talk about solving world hunger or predicting weather to the ultimate, to that level of fine grain. We're going to constrain the problem just a little bit to what we're talking about here at the SpringOne Platform Conference, and that is all around cloud native. Cloud native developers that are working both in the infrastructure space and the application space. So when we talk about cloud native, let's kind of circle back on what some of the complexity around cloud native might be. And I like to say that cloud native software is what I describe as software that is highly distributed and experiencing constant change. It's not the embedded systems that I worked on when I first started my career. Highly distributed, experiencing constant change, whether it's constant releases, like we just heard Barbara talk about, 500 releases all the time, or whether it is actually the infrastructure that's changing out from under our feet, we've got constant change. So we are going to talk about principles, and we're going to back those principles up with some very concrete examples. And we'll go through these 4 principles here. Now, the order isn't really that important, and we showed them in a circle because they're actually quite related to one another, and you'll be able to pick up on those relationships as we go through. But again, I want to emphasize that we're going to talk about things from a principle perspective, as well as then how you can actually start realizing those principles in practice. And that's where Mark is really going to help out. So again, when we go through those things, this applies to both all of you who are dealing with the platform side of things, the infrastructure, as well as those of you who are building the applications that run on top. And Mark is going to give us examples that fall into both categories. So it's all inclusive. You're all being covered. All right, let's talk about that first principle. The first principle is one of immutability. Now, as a programming languages geek from my days in the university and since then, and some of you may have heard me riff on functional programming versus iterative programming. And I've talked about how in functional programming, really, it's not so much that you have functions that you can pass around. You can pass around functions and still be doing imperative programming. The hallmark of functional programming that is the most important is that you are not side-effecting variables. You create variables, but they're immutable. And when you have immutability, all sorts of magical things happen. Now, as we start to get a little bit closer to the problems at hand today, you've heard about things like immutable infrastructure. You've seen or you're using pipelines to make sure that there is a process that is going to create an immutable artifact that I can then deploy into my immutable infrastructure. And what that's really doing is supporting repeatability. So immutability and repeatability are incredibly intertwined.
OK, so let's begin by talking about immutability of the deployable artifact. KPack is the open source project that is the foundation for Pivotal Build Service. And I'm not going to go through all of the detail here, but at a high level, you can consider this to be a system that watches for those constant changes that are happening in your code and in your build packs, patches applied to your base image, dependency updates, and so on. And anytime those changes occur, this can produce a new build. But what's important on this slide is that you see there are multiple instances of the build. We're not updating an existing build with the changes. We're creating a new build. And so that is what enables the repeatability. Each of those is immutable. We can go back to a previous build if we need to. And when you're running a highly distributed system of components, for each of those components, you can track exactly which build, down to the git commit and the build pack image that was used to create that instance. So that's on the infrastructure side. The same concept applies when you consider your application domain as being a series of events for different kinds of things that can happen in that domain. Each one of those occurrences is an immutable fact, right? So when you have an item added to a shopping cart, you don't remove that, you don't delete that fact. You create a new item that is the removal later. So that way, you're continuously appending in the same way that we're creating continuous builds within the KPack. And I just want to point out two things on this slide here from this example user activity. I think the first one is the unfortunate fact that the Spring Cloud Sloth project was very short-lived. If you were at SpringOne a few years ago, you know what I'm talking about. Despite Josh Long's efforts, it never made it onto the Spring Initializer. But on a more serious note, the Cloud Native Patterns book, this is Cornelia's new book. And if you like the concepts that we're talking about today, you want to see how they apply in much more detail, then I definitely recommend adding that book to your cart.
Oh, Mark, thank you. I wasn't expecting that shout out. All right, so let's move on to the second principle. The second principle is reactive. And I love this picture. These are drones. And if you hadn't seen these drones before, this one in particular is from Burning Man. But most of you probably saw the drone show, the light show that happened at the last opening ceremonies of the Olympics. Pretty amazing. Now, if you again think about this notion of determinism, could we program each one of the drones? And by the way, there were over 1,200 drones flying up in the air at the last opening ceremonies. If we want to deterministically program those and ahead of time assume that we know all of the variables that are in there, we wouldn't have had the light show that we did. Changing weather conditions, wind gusts, all sorts of things can have an effect on the way that each one of those drones is flying. So the principle there is really that we need to be more reactive to the things that are around us.
OK, so if we turn to the application domain, the infrastructure, and think about reactive, this on the left-hand side basically depicts what I talked about with KPack earlier, taking build packs, updates, code commit updates, and creating builds from those. But what we can also add, once we have these builds, we can add another process that is reacting to the new builds and creating deployment manifests. And what's important here is that these are modular. They're autonomous processes. It's not a monolithic continuous delivery system. And so we can extend this functionality easily by, say, adding another component in the middle of these that does image scanning so that we don't deploy something if there's a vulnerability. On the application side, we can obviously apply this same model to those event streams. And this example shows using Reactor and its Flux model, which represents a stream. And Reactor provides support for a wide variety of operations that you can perform on streams, including joins as well as windowing operations, which would both be relevant in a use case like this where we're trying to correlate ads with purchases, or the viewing of ads with the purchases. So you'll hear much more about Reactive shortly, but that's a Reactor, the project. That's an important capability that we support.
Awesome. All right, so the next principle is one of reconciliation. So just like we can no longer assume that everything is going to remain static. That was always a fallacy, but we used to build our systems and manage our systems in such a way that we thought things were going to reach some level of stability and stay stable. Instead, what we're doing is we're constantly diverging and coming back together and diverging and coming back together. And at the core of this notion around reconciliation is the new principle, and this is becoming more and more familiar, is this notion of actual state versus desired state. And what this acknowledges, the principle that this acknowledges, is that in this world now, we are never done. Done is a fallacy. There is no such thing as done. It's constantly a check of actual state versus desired state. Yes, sorry, one more slide from Cornelia. So at the core of that, by the way, is a declarative programming model. So when we talked about this before, we talked about the deployable artifact being immutable, the target environment being immutable, the deployment process being immutable. Now, if you want to change that deployment then, what you do is you declare what you want the deployment to look like in the future. And then you're comparing that to the actual state. So that's what we mean, and the declarative model is very, very key on that. Thanks, Mark.
Okay, so we can think about reconciliation in infrastructure by looking at Kubernetes itself. Kubernetes is designed as a layered system of resources, and the reconciliation of each of those happens in a way that can cascade declarative state to more fine-grained resources. So for example, a pod in Kubernetes is the atomic deployment unit that ultimately gets scheduled on a worker node. But you rarely interact with, you rarely as a developer would declare your desired state at the pod level. Instead, you might enter the system at the deployment level. And a deployment has a reconciler that reads in that declared state and creates a replica set. The replica set will manage that number of pods that you've requested. The replica set reconciler creates those pods and also watches those pods. So when something crashes, it's able to create a new instance so that it's always trying to satisfy that desired state. Now, when these pods are coming and going, crashing or scaling elastically, it's also important that you abstract those from your application code in terms of the endpoint that you're routing to. And that's where the service enters the picture. And so it's another piece of desired state you can specify using a label selector to expose the endpoint for a given set of pods, and that will always ensure that it's only routing to pods that are actually ready to handle requests. And on the application side, this shows an important principle when you have a use case that you can model as an event log, and you're using that event log as your source of truth, then you can generate the database view from that rather than using the database as the source of truth. And so here we see our cart updates, and they might be coming from different devices, right? If we had been updating a database directly, then when my mobile app is offline, but I've made changes to the quantity in the cart, when that comes back online, I wouldn't be able to easily reconcile that state. But in this model, since every single event is being recorded, then the reconciler can catch up with those events when it comes back online. And this idea, I think, is even more interesting when you look at something like inventory management. There might be a number of different systems that are emitting events that are relevant for the inventory. And rather than having the shipment system and maybe in every warehouse there's a monitoring system for recording damages, Rather than having all of those systems share some database where they're updating the state directly and having contention, instead they can just emit these events, and a centralized reconciler can keep the inventory state up to date. And this allows them to operate on different time schedules. Those warehouse applications might operate in batches and just send a stream of events once a day, and the reconciler can react to those when those happen.
Excellent. So then the final principle that we want to talk about is composition. All of these things are composable. Going back to the drone example that we were talking about earlier, we talked about how each one of the drones needs to be reactive to the stimuli around it. Well, some of the stimuli around it are the other drones that are flying as a part of the whole fleet. So that's what allows us to take a whole bunch of independent drones and actually create an image of Olympic rings or of a snowboarder. So composition is really where it all comes together.
And in the infrastructure, again, we can look at Kubernetes. Kubernetes is not just a container scheduler. It's also, it provides an extension mechanism through a concept called custom resource definitions. And revisiting KPAC, we see here on the top right that KPAC is itself modeled as custom resources, each one having its own reconciler. And we see Kubernetes on the bottom right, as I described earlier. Those resources each have a reconciler. Now, on the left-hand side, I've added Riff, which is the open source project that the Pivotal Function Service is built upon. And the way that Riff works is you declare your desired state at the level of a function pointing to your source code, and then the reconciler for function creates a image, the KPAC image. And so now we have a system that's automating the builds for every time I have a change to either the build pack or the source code for my function. And the status of those builds in terms of the latest image is always reflected in that function. So when I want to deploy that function, either as an HTTP endpoint with the deployer or as a streaming processor with the processor resource, those will refer back to that function and be able to update the deployment in Kubernetes every time there's a change in the build. And so on the application side, once you have this model, then you can create these PFS functions. You can use projects like Reactor or other languages as well and create an autonomous composition of different reactive processors. They can consume at their own rate. They can scale independently. And if one node fails, it's not going to cause cascading failures to others. It's just when it eventually comes back online, everything else will catch up in the system. And by sharing these events, having these reactive processors, consuming from those events, managing their own offset into the event log rather than destructively consuming, we can add new processes to this system that we hadn't thought about originally. So here we have a recommendation engine, the add conversion, correlation, the inventory management, and so on. And so you can create these composed systems of highly distributed reactive processes.
Awesome. All right. So to sum it up, these are the 4 principles that we covered. Immutability, the concrete takeaway is go ahead, use variables, but once you set the value, it never changes. That's what immutability is about. Reactive, stop thinking request response. Sure, there's a place for request response still, but start thinking more from a reactive perspective. How do I program my systems in such a way that I'm actually ready at the waiting for other stimuli to come in? Reconciliation, the main takeaway I want you to take away from that is APIs are not imperative anymore, they're declarative. Let the systems do the steps. And then finally, composition is something that we've always done, right? Even years ago, 30 years ago when I was in school, composition was a main thing. But what's happened is that all of these other elements, immutability, reactive, reconciliation, are all having downstream consequences on the composition. So the way that you do composition is affected by those things. So that's the final takeaway, is think about those things, start thinking differently, programming differently, and we wish you a lot of fun. Thanks so much.